This lab is called the charge transfer complex between iodine and acetylene.
So I'm going to talk to you about the charge transfer lab, and this is a reaction between acetylene, and acetylene is a methyl substituted benzene ring. Okay, and it reacts with iodine. Iodine is simply, I2, II. And it forms something we're just going to call a charge transfer complex. And in this complex, a negative charge, or part of a negative charge, is transferred from the acetylene to the iodine, which is the acceptor. So we have the donor and we have the acceptor. And we're going to study this equilibrium. So if this was general chemistry, we would we could set up the equilibrium using what I used to call in Gen Chem an ice chart. But whether you had me or not for Gen Chem, this I simply means initial concentrations, which the initial concentration of acetylene we just call MS0. The initial concentration of iodine, I20, and we have no complex at the beginning. And then we let X equal the amount of acetylene or iodine that react and the amount of complex that forms. It's all the same because it's 1 to 1 to 1. So that at equilibrium, MS0 minus X is the concentration of the acetylene, I20 minus X, the concentration of the iodine, and the complex simply has a concentration X. So we could write the K equilibrium expression as X over MS0 minus X times I20 minus X. Okay, now, when we do this experiment, what we're doing actually is we are going to make several solutions of different initial concentrations of the acetylene. We're going to keep increasing it. And as we do that, as we increase this, but we leave this constant, we're going to push the equilibrium a little bit over. Okay, so we're going to be forming more and more complex. And so we'll have different concentrations of acetylene, and the way we are going to detect the complex, okay, is we're going to detect the complex by UV vis absorbance. Okay, now a graph that's important for us to take a look at. Let me go. Okay. So what I have here are the UV spectra. The wavelength here is on the x-axis, so this part is a UV, okay, and this part is a visible. And the black line here is the visible spectrum of iodine. It absorbs, it has a kind of a weak absorbance band with a maximum around 540 or something like that. And the purple line is the acetylene, and you can see it really doesn't absorb at all in this range, and it sort of starts to absorb a little bit in the low 300s. But when these two are put together, a new band appears, and that is this red band here, and we call this the charge transfer band. And you could see that it's got visible absorbance, this red bunch here, but it's slightly shifted from the iodine, so the solutions will actually have a different color than the pure iodine, which is sort of more purple and becomes more pink as we make the charge transfer complex. But very importantly, there is this nice peak here at 330, and here nothing absorbs except that charge transfer complex. Okay, so it is the absorbance at 330 that gives us information on the concentration of complex. Okay. All right, so now I'm going to go back to where I was before. Okay, so this is what I have. Here's my equilibrium constant expression. And we detect the complex by UV vis absorbance. A equals EB times the concentration of the complex, which is, by the way, X, right? So that means X is A over EB. And so what I'm going to do is plug in that for X here, here, and here, except I don't need to plug it in here. So first I'm going to talk a little bit more about this guy here, ms0 minus X. And the reason I'm talking about this is because I can neglect this X. And that is because we run these experiments with the concentration of acetylene much greater than the concentration of iodine. In fact, this is approximately like around the order of 10 to the negative fourth molar, whereas this is about 1 molar. So what you can see is if you have this reaction, okay, and this concentration is 10 to the minus fourth molar, and this is between 1 and 3 molar, that even if all of this were to react, which it doesn't, this is an equilibrium, but even if it did all react, that would have no effect on the concentration of the acetylene. So basically, the concentration of iodine is so small that the concentration of acetylene is basically constant and equal to the initial concentration. So that means if I go back to this equation here, that I can say that this is approximately ms0, and it's a very good approximation. It's really within the significant figures. We can't do any better than that. So we can then say that the K is equal to X over ms0 times I20 minus X. And we have a really much simpler equilibrium constant expression. Okay, so now what I'm going to do is take and put in A over EB for X. Did I do that here? Let's see. Yes, A over EB for X over ms0 I20 minus A over E. It looks really like I'm making this worse, not better, okay? But that's not the case, all right? So first thing I'm going to do is I'm going to cross multiply, right? When I do that, I get ms0 I20 minus A over EB times K equals A over EB. And if you like do algebra, you say, okay, I'm going to get rid of that EB. Okay, so I'm going to cancel it here. So I have EB ms0, and then we put the K there as well. And now I'm going to multiply that. I'm going to multiply out, so that I20 minus EB ms0 K A over EB equals A. So let's see what I got here. I can cancel my nice EB. And so, yeah, I'm pretty much done. I'm just going to sort of reverse the way I wrote this. I'm almost done. Equals EB ms0 K I20 minus ms0 K A. Okay, I just rewrote it, putting the A on the left. Now I'm going to divide both sides by that initial methyl salicylate concentration. Okay. So I have A over initial concentration of acetylene, methyl salicylate. I do another lab with that, acetylene. So we're going to examine this equation as soon as I've written it. Okay, so first of all, let's figure out what are constants. Over the whole course of the experiment, epsilon is a constant. It's the molar absorptivity or the molar extinction coefficient. It depends on how strongly that charge transfer complex absorbs light. B is another constant. B is actually 1 centimeter. It's the path length. It's the width of the cell. Oh, could we call this the molar extinction coefficient? Okay, and of course, the equilibrium constant is constant at a given temperature. Okay, so that's constant. MS0, this varies. Remember I said that we're going to run this experiment with several different methyl salicylate initial values. So we'll have a whole bunch of different ones of these, actually 7 of them. And then the absorbance will be measured that corresponds. Okay, several values of these. But you notice if you take A over MS0, if you plotted that on the y-axis, okay, that these guys are all constants, and this guy is a constant. So we actually have a y, and this is a variable. This is, we plot that on the x-axis, okay? Then we would have y equals b plus m x, where the slope is m, is the negative of the equilibrium constant, and the intercept is a whole bunch of constants. Okay, so we have, what we have done, this is, there's a term for this, we have linearized this KEQ expression. And we have figured out how we can use our data. This is the data for our initial MS concentration, initial acetylene concentration, and the absorbance of the complex. We have figured out how to use that data to extract the equilibrium constant. And also, once we have the K, so the slope is minus K, so K is the negative of the slope. We also know that the intercept is EBKI20, but all these things, K we can get from the slope, B is a constant, I20, we all know those things. So we can actually take the intercept and divide it by BKI20, and that gives us the epsilon. So we could actually solve for epsilon as well. So basically in this experiment, we're going to get K by this method, but we're going to do it at 2 temperatures. Okay. So we're going to get K by doing the experiment at 25 degrees C and at 35 degrees C. Okay, we'll call this K1, it's K at T1, and K2, which is K at T2. And there's an equation. Ooh, I hope I don't get this wrong. Okay, here it is. I hope I don't have it back. Let's just make sure. I wrote it a slightly different way here. This is the lab handout. Here it is. There we go. So let's see. Well, let's just use it this way. It doesn't matter. We're not deriving it here. T2 minus T1 over T2 T1. So this is an equation. And basically, it tells us that if we have this log of this temperature, this equilibrium constant ratio at 2 different temperatures, and of course, we'll know what all these temperatures are, and we'll know the gas constant, we'll be able to solve. So this gives us delta H for the reaction, the enthalpy change, a standard enthalpy change for the reaction. And we also know from chem, which you learn at the very end of the semester, and we'll learn later in PChem, of course, that we can get the free energy change from the K, and we would use this at the 25 degrees C, and this will give us delta G at 25 degrees C. So we'll be able to get the delta G. And then using this formula, since we will by this time know delta H and delta G, and we'll know the temperature, we use the 25 degrees C or 298 Kelvin, we'll be able to get the change in entropy. And we'll be able to put that together and try to understand a little bit more about this reaction.
Okay, so here is the setup that I'm going to use to prepare the solutions for the charge transfer lab. You can see that I have 7 volumetric flasks numbered from 1 to 7. You can sort of see that. And here are my stocks. I have 2 stock solutions, a 4 molar solution of acetylene and cyclohexane, and then I have pure cyclohexane, and here in the middle I have an iodine solution. It's a much smaller concentration, 1.45 times 10 to the minus 3 molar iodine and cyclohexane. And so what I'm going to do is I'm going to pipette a certain amount of each of these solutions into these flasks. So every one of them is going to get 4 milliliters of the iodine solution, okay? Each will get that 4 milliliters of the iodine in cyclohexane. And then into each, they will get different amounts of the acetylene 4 molar solution, also in cyclohexane. The first will get 0, the second will get 2, 4, 8, 12, 16, and 20 milliliters. So I'm going to do that pipetting. I'll show you some of it. I don't think I have to show you all of it. All right, I'm going to start pipetting 4 milliliters of this iodine solution into each one of these flasks. You can see the nice purple color of the iodine. Oops, missed the mark from all I'm talking. Take 3 here. I'm just putting it in. I'm not going to show you this 7 times. It seems excruciating to see it done one after the other. So suffice it to say, I'm going to do this 6 more times. Okay, so now you can see that I have pipetted some of that iodine solution into each of these 7 solutions. That was the easy part because all of those were the same amount. Now for the acetylene solution in cyclohexane, I've got to put 0, 2, 4, 8, etc., all different amounts, and that's going to be a little harder, but I'm going to use a graduated pipette. Okay, so now I'm ready to do the acetylene. So as I said, I'm going to add all different amounts of acetylene according to the direction. So the first solution is easy because it's 0, so 0 acetylene. So now I'm going to put 2 milliliters into the next solution. But I think I'm going to fill my pipette because I'll be able to do at least 2 or 3 solutions at once with this graduated pipette. Let's see how this goes. We'll go down to the 0. Okay. The first one I'll put 2. Can't go very far into this. Makes it a little harder. Okay, 2. The next one I'll put 4. 3. 4. 5. 6. I don't have enough to put 8, so I'll have to go back in again. I'll have to bring the camera around and show you how the color has changed. One, two, three, 4, 5, 6, 7, and 8. Okay, I'm supposed to add 12 to the next one, so I think I'll do it, maybe I'll do 10 and 2. Zero. Eight. 9. 10. And 2. Six to 8. Seven, 8. Good. 16 and 20. I'll try for 10 and 6. A lot of waiting in chemistry, right? I could call it skilled waiting. 10. Oh, wow, it's right on the 3. So we'll go from the 3 down to the 9. 4, 5, 6, 7, 8, 9. And 20. Well, this one's going to be fun. 10 and 10. Nine, 10 more and I'm done. Well, I have to bring everything to the mark with cyclohexane, and after that I'll be done. Seven, 8, 9, 10. Good. All right. Close up these solutions. All right. what I'll do is I'll pour it so it's close to the mark, and then I will use a pipette to finish it off. And the mark is different on every one of these, so. This is the first one, and it has that deep purplish kind of color. The others are a little more, I don't know, they turned a little orangey. Okay. Just gonna do this. I think I'm gonna turn the camera off because this is like about as boring as watching paint dry. Hi. Well, apparently the video that I made, that I thought I made, showing filling these to the mark with the solvent didn't exactly take. So what I did was, you know, I put the right amount of acetylene in each one. I started to show you that. I did that. I think I might have gotten to the end of that. I'm not really sure. Then I just filled each one of these to the mark, and then I inverted and mixed each one 10 times. And now I'm ready to take the spectrum of each one. There's a nice range of colors there. Mostly the same color, but a little bit interesting. Okay. The first one is that pure purple. And then after that, they get less pure purple.
Now we come to the part of the lab where we actually have to record the spectra of solutions 1 through 7 at each of those 2 different temperatures. We're using a very, almost brand new Cary 3500 UV-Vis instrument, which is capable of actually measuring 7 solutions spectra at the same time. So we'll do the 7 solutions at one temperature, then we'll do the 7 solutions at the other. Before we actually run the spectra, we're going to run what's called a baseline. Okay, in one of the sample compartments, the reference compartment, we put pure cyclohexane. And in the other compartments, when we run the baseline, we also put just cyclohexane. Doing a baseline allows the instrument to take into account any differences between the cell compartments, and those are all subtracted out when you then put in the solutions and run your actual samples. So what we'll be doing is we'll be taking a baseline, taking a baseline at 25 degrees C. Then we'll do a baseline at 35 degrees C, followed by replacing the cyclohexane with all the samples and running the spectrum of each sample all at the same time at 35 degrees C, and then going back down to 25 degrees C and doing it again. The reason we can't do it 25, 25, baseline samples, and then 35, 35 baseline samples is because of the software, which is actually the weak link with this instrument at this point, because it is like the first rendition of the software. It's a brand new instrument. So there are some problems that I had to sort of get a workaround to literally work around. Okay, so now we're in the program and we chose scan, and we're going to go into the method part of the program, and then we're going to put in the wavelength, and we want this to go from 750 nanometers to 300 nanometers. Let's see, the next thing we're going to do, we're going to make sure that we're using our multi-cell Peltier. That's a temperature controller. We're going to go into the next compartment here. And, this is crazy. I have 7 samples, but notice, and I'm doing a baseline as well. So I'm going to choose baseline here eventually. But why did I put 21 in there? That is the interesting question. Okay. So the reason I do that is because this instrument, the software hasn't been out a long time, and it's really got some difficulties. And every once in a while, for some reason, it seems to run the sample before I want it to. And if you've told it that you have 7 samples and it runs the sample when you have baseline, when you have solvent in there, there's really no way to go back and have it do it again. So that's why I might choose to put 14, which means if it took the first 7 and it was baseline, I could just have the next 7 be the sample. And if that happens twice, I could do it a third time. So I sort of arbitrarily chose to put 21 as the, I give myself 2 chances to get this right. So that's the basic idea behind that. It's kind of a workaround for this kind of cumbersome and not very good software, because the instrument is wonderful, but the software, we're kind of the guinea pigs on that. So now I'm going to start this experiment for sure, like for real. And to do that, I have to adjust the temperature. So I'm going to go and change this temperature to 25 degrees C. Do that right now. Unfortunately, I seem to be having some difficulty with that. So what I'm going to do is make sure that this instrument is actually hooked up. So in the upper right corner, I'm going to click over there, and you'll see that now I get to connect the instrument, and now I believe I'll be able to apply this temperature. Okay, so once I've applied that 25 degrees, I get this nice display. There's actually 4 separate temperature controlling devices. The red temperature is what it's set at, and the black temperature is what the cell temperature is, and it's heading for that red set point. I'm just going to check out, check that I have those 21 samples ready, that I don't intend to use more than 7. But as soon as I click that forward arrow, it prompts me to give a file name. So I, put my initials on it. I say charge transfer. And okay, as soon as I do that, when I hit OK, which I just did, now it's running that baseline, because now I have cyclohexane in every one of those cells, and each of those is leading to one of those lines. And of course, what the instrument wants me to do now is hit the OK button here. So in other words, it wants me to put my samples in next at 25 and then hit OK, and it'll run the samples. But I'm not going to do that. I want to show you here that if you run the cursor back and forth on the right there in the display, it'll actually tell you what the absorbance is at whatever wavelength you're at. Okay, so what I want to do is now get out of this program. So I sort of canceled that thing. I did not run the sample, and I went out back home, and I clicked on scan for a new scan, because now what I'm going to do is set the temperature to 35 degrees, because I still have those cyclohexane in those cells. I have the cells filled with cyclohexane. Again, I'm changing my number of samples to a ridiculous 21 in that crazy workaround, because the software is terrible. And I put in 35 degrees over here. I set the wavelengths too to be what they should, and now you see that the set point is at 35 instead of 25. Okay, and the temperature is not right yet, so I won't be able to run that baseline yet. So I'm just going to wait a little while. And here's a little bit later. You can see now the temperature is at 35, and as soon as I hit that white arrow on top, it's going to prompt me to give a file name. So I'm just going to wait for that to happen. I'm sure it'll happen any moment now. There it goes. Okay, and now I'm prompted to give a file name. It seems like I'm a little indecisive here. Like I want to make sure that everything is right. So I go back and look at the number of samples. Then I go and hit the arrow. And this time I actually put in the file name. This program is not very forgiving if you do something wrong, which is why I'm always double checking. So there's the file name. And as soon as I put that in, now you see it says sample instead of baseline. Oh, sorry, it said baseline again at 35. I'm getting a little, doing too many things at once here. Okay, so now I'm going to actually put my samples in and run the actual Spectra at 35. That's my next job. Hi, so I just ran a background, a baseline, I should say, for my 7 sample cells in here. And against the reference right in there. These are all filled with cyclohexane at 35 degrees. I did the 25 degree one previously.
And so now I'm going to run these samples, but what I have to do is actually put the solutions in them. So I'm going to take and remove these in order. 1, 2, they're all labeled in here. 3, 4, 5, 6, and 7. Now I'm going to fill the cyclohexane into the waste. I try to hold these by the corners or by the top, but I'm kind of in a hurry, so. All right, now let's just go to do the solutions one at a time. All right, let's see. 1. I'm going to give a rinse. All right, that's one. I'm not going to show you all of these. I'll show you the first couple. And it's pretty self-explanatory after that. I should want to get rid of the solution. Take this off. Clean pipette. Number 2. Rinse it once. I'll have to wipe these with Kim wipes also before I put them in the instrument. I'm going to put the cells in order. 1. Oops, that was in the compartment 2. 1, 2, 3, 4, 5. I already wiped them with Kim wipes. All right.
And now it's time to click on that little OK button and start the Spectra going. And this is what the spectrum looks like. Okay, so these are the very nice looking 7 spectra of solutions 1 through 7. And I'm looking at that short wavelength peak at around 330. And the solutions go in order from 1 to 7. The absorbance increases as we go from 1 to 7 because the mesitylene concentration is increasing. You see there's a shift in that colored peak, the which I've just blown up in the 500 range. But what we're really focusing on is the peak at the left. And all the wavelengths for the different samples, so sample 1 is solution 1, etc., are all on that chart. And that is the data that you're going to use to analyze, for your analysis in this lab. And I should say at 35 degrees C, because this data was taken at the higher temperature. And now I'm going to, we're back to the other file, and I've waited for the temperature to come down to 25 degrees C. And when it does, I'm going to hit OK, because the samples are already in there. And then I will get my data at 25 degrees C. And this is what the spectra look like at 25 degrees C. Again,
Solution 1 is on the bottom and solution 7 is on the top. And the only difference is this is at the lower temperature. And so this is what the spectra look like when they come off the instrument. And then I put them in PowerPoint and actually blew up the sample spectra, and I blew up that little table with the absorbances at the different of the different solutions, and that's shown here. Okay, and if you look closely, you could see that at 25 degrees, all of the absorbances, those are the Y values there. Y value is absorbance, X is wavelength. All of those absorbances are a little higher at the lower temperature. That's something you should make a note of. As the temperature went up, the absorbance went down a little bit. What does that mean about the equilibrium constant? Or actually, maybe I should have said, what does it mean about what happens to the equilibrium constant as the temperature goes up? Okay, and you should be able to conclude something from that, which actually was taught in general chemistry, about the sign of the delta H.
And that's it. That was the charge transfer lab. Thanks for your help, Kathy. And I hope everybody understood this video.